Ура. Кажется, работает. Okay, so today our first goal is to prove the homotopy invariance of K0 for Banach algebras. First of all, let's briefly recall what we already know from the previous lecture. So suppose that A is a unit of Banach algebra. And suppose that E and F are two idempotents in A. So we now have many equivalence relations on idempotents. So first of all, recall that we introduced the homotopy equivalence between E and F. So we say that they are homotopic and write the symbol if there is a continuous path in the set of idempotents which connects E to F. So in other words, this means that they sit in the same path-connected component of this space. Actually, this equivalence relation makes sense in any topological space. And we proved that if two idempotents are homotopic, then they are similar. And we already know that if two idempotents are similar, then they are algebraically equivalent. In general, the converse implications are not true. There are some counterexamples. But they are true if we pass to 2x2 matrices. So let me write such dashed arrows, which mean that we have such implications after passing to 2x2 matrices. So as a result, if we replace A by the algebra of infinite matrices over A, then if we consider idempotents in this algebra, then all three equivalence relations are actually the same. Homotopy, similarity, and algebraic equivalence are actually the same equivalence relation. And we can use any of them to define K0 of A, which is quite useful. Let's now introduce the notion of homotopic homomorphisms between Banach algebras. So we have the following definitions. The following definition: if we have two Banach algebras, A and B, and two continuous homomorphisms, phi 0 and phi 1, from A to B. Continuous homomorphisms. We say that they are homotopic. Phi 0 and phi 1 are homotopic. And we write the following, use the following notation. If there exists a continuous homomorphism, let's denote it big phi, from A to the algebra of continuous B-valued functions on the closed unit interval 0, 1. So clearly this is also a Banach algebra for the supremum norm, such that the following diagram commutes. So here we have our map big phi. And we have two evaluation maps from this algebra to B, namely the evaluation at 0 and the evaluation at the identity. So this composition should be equal to little phi 0, and this one should be equal to little phi 1. So this diagram is commutative. And in this case, we say that big phi is homotopy between phi 0 and phi 1. Well, initial question is how is this relation related to our earlier definition of homotopy of points in any topological space? And the following exercise gives an answer. Let's consider the set of all Banach algebra homomorphisms from A to B. And let's equip this set with a topology in the following way. So here Hom AB stands for the set of all Banach algebra homomorphisms from A to B, that is, continuous algebra homomorphisms. So we equip this set with the topology of pointwise convergence. This means that this is the topology induced from the space from B to the power A, from the space of all maps from A to B. And this set is equipped with the product topology. So we consider many copies of B and take the product topology. Then, first of all, we have a bijection. A bijection between the set of all homomorphisms from A to this big algebra, from A to the algebra of B-valued continuous functions on 0, 1. And the set of all continuous maps from 0, 1 to Hom of AB. That is the set of all continuous paths in the space of homomorphisms from A to B. So here this set is topologized in this way. And as a corollary of this bijection, we see that two homomorphisms from A to B, phi 0 and phi 1, are homotopic in the sense of this definition, even only if they are homotopic as elements of this topological space, of the space of homomorphisms from A to B. That is, there is a continuous path in the set connecting phi 0 to phi 1. And explicitly, this means that there is a family, let's denote this family by big phi t, of homomorphisms from A to B, indexed by points in the interval, a family of homomorphisms from A to B, of course continuous homomorphisms from A to B, such that, first of all, big phi 0 is little phi 0, big phi 1 is little phi 1, and we have the following continuity property that for every little a in A, the map which takes every point t into the interval 0, 1 to the element phi t of A, which sits in B, is continuous. So this property is equivalent to the continuity of the respective path for the topology of pointwise convergence on this space. Okay. In a special case where A and B are the algebras of continuous functions on compact Hausdorff topological spaces, this notion of homotopy. A question? I know. This notion of homotopy reduces to the usual notion of homotopy of maps between topological spaces. So this is a simple exercise. If x and y are compact Hausdorff topological spaces, and phi 0 and phi 1 are continuous maps from x to y, then they are homotopic as continuous maps in the usual topological sense, that is, as continuous maps from x to y, if and only if the induced homomorphisms between algebras of continuous functions, phi 0 dot and phi 0 1 dot, are homotopic as homomorphisms from C of y to C of x. Okay, now we have the following theorem. So this is our homotopy invariance result. Homotopy invariance of K0. So suppose we have two homotopic binary algebra homomorphisms, phi 0 and phi 1, from A to B. I claim that they induce the same map, the same homomorphism of K0 groups. Phi 0 star equals phi 1 star as maps from K0 of A to K0 of B. Well, let's now prove this result. First of all, let's observe that we can assume from the very beginning that the algebras are unital and the homomorphisms are also unital. We assume that A, B, phi 0 and phi 1 are unital. Because if they are not unital, we extend these homomorphisms to extend all homomorphisms in this picture to the unitization of A. Otherwise, extend big phi to a map from A plus to the algebra of continuous functions with values in B plus. And so now all homomorphisms and all algebras become unital. The only point I'd like to stress that this algebra, which is shown here, is not the same as the unitization of this one. This one is bigger. But actually this doesn't matter because the universal property of the unitization of A immediately gives us this map, this extension. So we reduced everything to the setting of unital algebras. Okay, now also let's recall that K0 of A, if A is not unital, is defined as a certain subgroup in K0 of A plus. So if the induced maps between the K groups of the unitizations are the same, then these two maps are also the same. Okay, now so let's now take an idempotent, as noted by E, let E be an idempotent in the n by n matrix algebra over A. And let's apply big phi to E, and the resulting element will be denoted by big F. So this is phi of E. So this element, where does it sit? It sits in the m by n matrix algebra over this algebra. So this is an idempotent in the algebra of continuous b-valued functions, in the matrix algebra. In the matrix algebra over the algebra of continuous b-valued functions on 0, 1. So what can I say about this algebra? First of all, let's observe that this algebra can be identified with the algebra of continuous functions on 0, 1 with values in the matrix algebra Mn of B. So a matrix of continuous functions with values in B is the same as a continuous function with values in n by n matrices over B. This is rather obvious. And finally, let's observe that the set of idempotents in this algebra is nothing but the set of those continuous maps from 0, 1, whose values sit in the set of idempotents of Mn of B. So in other words, this is just a set of continuous paths of idempotents in Mn of B. And F is an element of this set, so it is a continuous path. And let's now look at f of 0 and f of 1. So by looking at this diagram and applying it to E, we see that f of 0 is little phi 0 of E, and f of 1 is little phi 1 of E. So this path connects these two idempotents. So we deduce that they are homotopic. Phi 0 of E is homotopic to phi 1 of E in Mn of B. But we know that homotopic idempotents give us the same element of the K0 group. So the respective elements of K0 are the same. In K0 of B. And basically this completes the proof. Formally we have shown that these two maps are the same on the equivalence classes of idempotents, but of course we remember that K0 of A is generated by equivalence classes of idempotents. And so these homomorphisms are the same everywhere. As a simple corollary, we obtain the homotopy invariance of the topological K-theory. So if we have two compact Hausdorff topological spaces X and Y, and two continuous maps from X to Y, then if they are homotopic in the usual sense, then the induced homomorphisms between K0 groups are the same. This follows immediately from our theorem and from this exercise. Before we discuss other corollaries, let's introduce some terminology. A definition. We say that a continuous homomorphism phi from A to B, so as before A and B are Banach algebras, we say that phi is homotopy equivalence. Homotopy equivalence. If there exists another homomorphism psi from B to A, such that the composition psi phi is homotopic to the identity map of A, and phi psi is homotopic to the identity map of B. So this definition is absolutely similar to the respective notion of homotopy equivalence between topological spaces. And we say that Banach algebra A is contractible. If it is homotopy equivalent to the zero algebra. More explicitly, this means that the identity map of A is homotopic to the zero map of A. And as a corollary of our homotopy invariance result, we see that if phi is a homotopy equivalence from A to B, then the induced map of K0 groups is an isomorphism. An isomorphism. And if A is contractible, then K0A is trivial. K0A is 0. Well, it's again a simple exercise to show that the homotopy equivalence of Van algebras is compatible with the notion of homotopy equivalence between topological spaces in the following sense. So we have the following exercise. If X and Y are compact Hausdorff topological spaces, and F is a continuous map from X to Y, then F is a homotopy equivalence if and only if the induced map, the induced homomorphism between the algebras C of Y and C of X is a homotopy equivalence in the sense of this definition. This is rather straightforward, but not entirely straightforward, because again, our homomorphisms are not assumed to be unital, and are not assumed to be star homomorphisms. So formally, we cannot apply the Gelfand-Nalmec duality in a straightforward way. So we must do some auxiliary tricks, but anyway, we have this equivalence. And of course, this implies that the respective map F star between the K0 groups is an isomorphism. And as a special case, in particular, we see that if X is contractible as a topological space, which means that it is homotopy equivalent to a point, it's homotopy equivalent to a point, then K0 of X is isomorphic to the integers, and explicitly this isomorphism takes every natural number n to the equivalence class of the trivial bundle of dimension n. If we now compare this and this, we see that, and this is an important point, that the notion of a contractible Van algebra doesn't entirely match the respective topological notion of a contractible topological space. In fact, let's do the following little remark. If A is a unital Van algebra, and if there exists a unital homomorphism from A to the complex numbers, then A is not contractible as a Van algebra. Well, indeed, if we have such a homomorphism, we can look at K0 groups and observe that, first of all, clearly, since epsilon is obviously a retraction of algebras, because the section of obviously this map has a section, the map which takes the unit of C to the unit of A. So it is a retraction of algebras, and this implies that the induced map is a retraction of groups, and so K0 of A contains a direct summoned isomorphic to the integers. That is to K0 of C. And so, of course, this implies that K0 of A is not trivial, and so A is not contractible. And in particular, we see that the algebra of continuous functions C of x, where x is a compact Hausdorff space, is never contractible. Where x is a compact Hausdorff space, well, of course, x is non-empty. Because this algebra has many homomorphisms to the complex numbers, namely the evaluation maps are non-trivial unital characters. So this remark shows that there is no one-to-one correspondence between contractible topological spaces and contractible Banach algebras. And the reason is that our definition of a homotopy between maps and of a contractible Banach algebra are given in the non-unital setting. Nevertheless, there exists a certain relation between these two versions of contractibility. So I suggest you the following exercise. Suppose that X is a compact Hausdorff topological space, and let's choose a point x0 in this space, and let's consider the maximal ideal, let's denote it by mx0, in the algebra of continuous functions on x of those functions which vanish at x0. So this ideal is also Banach algebra, and it is isomorphic to the algebra of C0 functions at the on the complement of this point, x minus x0. So the question is, when is this algebra contractible? So I mean that it would be nice to give an answer entirely in terms of our space and the point x0. Give an answer in terms of some topological properties of x and x0. Let's now discuss a useful construction which always produces a contractible Banach algebra. So we give the following definition. If A is a Banach algebra, we define the cone over A to be the algebra denoted by CA. And by definition, this is the algebra of C0 functions, continuous and vanishing at infinity functions, on the half interval 0, 1 with values in A. So more explicitly, this algebra can be identified with the algebra of those continuous functions from the closed interval 0, 1 to A, which vanish at 0. Of course, the norm on this algebra is just the usual supremum norm. How is this construction related to the topological cone? Well, here's an answer. Suppose that X is a compact Hausdorff topological space. And let's look at the topological cone. Usually the topological cone is also denoted by Cx, but we have too many different meanings of big C, the algebra of continuous functions, the cone over Banach algebra. So to avoid confusion, let's denote the cone, the topological cone over X in the following way. So by definition, this is a topological space which is obtained as follows. We take the cylinder over X, that is the product by the closed interval, and take one of the bases of the cylinder and contract it to a point. So for convenience, let's take this base and consider the respective quotient. So this space has a natural base point, let's denote it by V0. This is the vertex of the cone. This is the point which corresponds to this contracted base of the cylinder. The equivalence class of points in this set. The exercise is to show that the cone over the algebra of continuous functions on x over C of x is isomorphic to the algebra of C0 functions on the topological cone with the vertex removed. That is, with the algebra of those continuous functions on the topological cone, which vanish at the vertex. So this exercise relates the Banach algebra cone with the topological cone constructions. So now I claim that the cone over any Banach algebra is contractible. If A is a Banach algebra, then the cone over A is contractible. And the proof is very easy. We manufacture a very concrete homotopy between the identity map and the zero map of this algebra. So it acts from C of A to the algebra of continuous functions on the interval 0, 1 with values in C of A. And this map acts by the following explicit formula. If phi is a function in C of A, so we want to define phi of f. Phi of f is a function from here to here. So to define phi of f, we must show what is the value of this function in a point S belonging to the interval 0, 1. So this element, in turn, must be an element in C of A. And C of A also consists of functions. Look here. So to define this function, we must explain how to evaluate this function in a point T of the interval. And we define this number, this element, to be f of St. So clearly this is well defined because, first of all, this function, if we fix a little s, so the function is indeed in the cone over A because, well, if t is 0, then for every s this is also 0 and this vanishes. So this is, again, this is indeed a function in here. It is obviously continuous, and this map connects. Map is a homotopy between the zero homomorphism of the cone and the identity map of the cone, which is again explicit from our formulas. So explicitly, if s is 0, then this is f of 0, but f of 0 is 0. And so evaluating this at 0, we get the 0 map, and if s is 1, then clearly this is f of t, and we get the identity map of the cone. Okay, so the cone is always contractible. Let's now look at some special properties of K0 in the setting of C-star algebras. K0 for C-star algebras in terms of projections. So roughly what we are going to do is to look at the setting of C-star algebras and to incorporate some compatibility with the involution into our picture of the group K0 of A. Let's start with some definitions. Suppose that A is a unital star algebra and V, that's better U. U is an element of A. We say that U is, here we have three definitions. Definition one, we say that U is an isometry. If U star U equals 1. Next, we say that U is a co-isometry. If U star equals 1, which is not the same in the general case. And finally, we say that U is unitary if it is invertible. U is invertible, and U inverse equals U star. Which obviously means that U is an isometry and a co-isometry at the same time. An isometry and a co-isometry. The following exercise explains where the terminology comes from. It explains why such elements are called isometries, co-isometries, and unitaries. Suppose that A is a unital star subalgebra in the algebra of bounded operators on the Hilbert space. Star subalgebra, which contains the identity operator. Then an element U of this algebra is an isometry in the sense of our definition, if and only if it is isometry in the geometric sense. That is, if and only if it preserves the norm. The norm of U of x equals the norm of x for every x in H. Or equivalently, if and only if it preserves the inner product. The inner product of U of x and U of y equals the inner product of x and y for all x and y. Let's now look at unitary elements. So I claim that an element of A and operator little u is unitary, if and only if it is a bijective isometry. A bijective, or equivalently a surjective isometry. Well, an isometry is always injective, which is more or less clear from this definition. If it preserves the norm, then its kernel is trivial. So it is surjective if and only if it is bijective, and if and only if it is unitary in the sense of our definition. And finally, an element U of A, an operator. U is a co-isometry. If and only if there is a closed vector subspace, as denoted by H0 of H, such that U vanishes on the orthogonal complement on this subspace, and such that U restricted to H0 is an isometric map of H0 onto H. An isometric map of H0 onto H. In particular, it is surjective. And in this case, H0 is nothing but the orthogonal complement of the kernel. Well, it's clear that if our space H is finite dimensional, then all these notions are equivalent. This is a simple observation. H is finite dimensional, then an operator on H is an isometry, if and only if it is a co-isometry, and if and only if it is unitary. Because an injective operator on a finite dimensional space is bijective. But in the infinite dimensional case, these notions are not equivalent. And here is the simplest example of the situation. Let H be the little L2 space of square summable sequences. And let V denote the right shift operator on H. Right shift. Which takes every square summable sequence x1, x2, and so on to the following sequence. So it shifts by one position to the right and adds 0 to the first coordinate. So clearly, V is an isometry. V is an isometry because it satisfies this condition. So V star, the adjoint operator, is a co-isometry, simply by the definition of a co-isometry given here. So it's clear that from the definition that V is an isometry if and only if V star is a co-isometry. But they are not unitary. They are not unitary for the simple reason that V is not surjective. In fact, it's a simple exercise to show that V star is the left shift operator. V star is the left shift operator. That is, it acts as follows. Takes every sequence x1, x2, and so on to the following one. So it kills x1 and it shifts all the remaining coordinates by one position to the left. So clearly this map is not injective. It has a non-trivial kernel. Well, the following simple exercise gives us describes some simple properties of isometries, co-isometries, and unitaries. So suppose that A is a unital C-star algebra. Then if U is an isometry or a co-isometry, then the norm of U equals 1. This readily follows from the C-star property. Well, of course, we assume that A is non-zero. A is non-zero. If U is unitary, and we can say more. If U is unitary, then the spectrum of U is contained in the unit circle on the complex plane. So let's denote this circle by T. The unit circle are centered at 0. In general, it can be any closed subset of the circle. There are no restrictions. But if A is a non-unitary isometry or a co-isometry, if U is a non-invertible isometry or a co-isometry, then its spectrum is exactly the closed unit disk. That is the set of all complex numbers satisfying this inequality. The closed unit disk on the complex plane. Okay, let's now introduce some other types of elements in star algebras. suppose that A is a star algebra. At this point, we don't assume that it's unital. And we say that an element little p in A is a projection. If P is a self-adjoint idempotent. A self-adjoint idempotent. In Russian we say проектор. Почему-то очень многие любят говорить проекция. Ну, это дословный перевод, но вообще обычно, когда говорят про элемент, в русском языке с этим свойственно, говорят проектор. Так как это принято. By the way, I'd like to remark that this terminology doesn't entirely correspond to the terminology in the theory of operators on Banach spaces. So in the Banach space theory, by a projection, one usually means a self-adjoint, by a projection one usually means an arbitrary idempotent operator on the Banach space. Not necessarily on a Hilbert space and not necessarily self-adjoint. And self-adjoint idempotent operators on Hilbert spaces are usually called orthogonal projections in operator theory. But in the sister algebra theory, by projection, we usually mean a self-adjoint idempotent. So this is a standard terminology, and we will follow it. And we say that an element V in A is a partial isometry. If it satisfies the following property, V star V equals V. Well, let's first of all observe that the notion of a partial isometry generalizes all these properties given in our previous definitions. So every isometry is a partial isometry. Every co-isometry is a partial isometry. And every projection is also a partial isometry. Well, indeed, if, for example, if V is an isometry, then this product is 1, and we get V here. If V is a co-isometry, then this product is 1. And if V is a projection, then we have V, 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 but V is idempotent, so this is also V. So this is our first observation. And the second observation is that if V is a partial isometry, then so is V star, V adjoint. Just apply the involution to this equality and get a similar equality for V star. And of course, the converse is also true. The following exercise explains where the terminology comes from. Again, suppose that A is a star subalgebra in B of H, where H is a Hilbert space. Then I claim that an operator, P in A, is a projection, if and only if there exists a closed vector subspace, H0 in H, such that P acts as the orthogonal projection onto H0. That is, such that P restricted to the orthogonal complement is 0, and P restricted to H0 is the identity map of H0. And in this case, H0 is nothing but the image of P, and the orthogonal complement is nothing but the kernel of P. How about partial isometries? Well, they can also be characterized geometrically in the following way. Namely, an operator P in A is a partial isometry if and only if there exist two closed subspaces, H0 and H1 in H, such that V vanishes on the orthogonal complement of H0, and V restricted to H0 is an isometric map of H0 onto H1. An isometric map of H0 onto H1. And actually, in this case, H0 is nothing but the orthogonal complement of the kernel of V, which is, by the way, equal to the image of V star, of the joint. And H1 is exactly the image of V, which is nothing but the orthogonal complement of the kernel of V star. So geometrically, the picture looks as follows. We have two direct sum decompositions of our Hilbert space H into H0 and H0 orthogonal, and into H1 and H1 orthogonal. So V takes H0 isometrically onto H1, and symmetrically V star takes H1 isometrically onto H0, and these two maps restricted to H0 and H1 respectively are inverse to each other. And if we restrict them to the orthogonal complement, then they act as zero maps. So this picture represents the geometric picture of which explains how a partial isometry acts. Okay, now, a little but useful exercise which gives us some information about norms of partial isometries. If A is a sister algebra, and V in A is a partial isometry, then the norm of V is either 0 or 1. So in other words, if V is non-zero, then its norm is equal to 1. And actually, this property characterizes projections among the idempotents. So if E is an idempotent in A, then E is a projection if and only if its norm is either 0 or 1. Let's now characterize partial isometries in terms of projections. So we have the following proposition. Suppose that A is a sister algebra, and V is an element in A. Then the following conditions are equivalent. Condition 1, V is a partial isometry. Condition 2, V star V is a projection. And condition 3, V star is a projection. Well, this picture shows that this is quite convincing. So, at least in the case where A is already embedded into B of H, this picture can be used to give a very simple proof. But if we work with abstract sister algebras, then the proof is also quite simple. For example, to prove that 1 implies 2, we simply write the definition of a partial isometry and multiply it by v star on the left. And we deduce that v star v squared equals v star v. So v star v is idempotent and clearly is self-adjoint. So it is a projection. To prove that 2 implies 1, we use the C-star property. So we want to show that the element v minus v star v is 0, which means that v is a partial isometry. So we assume that this one is a projection, and we want to prove that this is 0. So let's calculate the norm, the square of the norm, by using the C-star axiom. So first of all, this can be written as v times 1 minus v star v. Well, we don't assume that our algebra is unital, but of course we can always embed it into the unitization and work with the identity in the unitization way. And by the C-star property, this is equal to the norm of the adjoint element of this, and the adjoint is 1 minus v star v star, this is the adjoint, times this element, which is v times 1 minus v star. And let's now look here. So v star v is a projection, so it is idempotent, and when we multiply these two elements, we get 0. So as a result, we get 0. So v is a partial isometry. And the equivalence, so now we now know that 1 and 2 are equivalent. And the equivalence between 1 and 3 is immediate because we simply apply the equivalence between 1 and 2 to the element v star. Apply the equivalence between 1 and 2 to v star. And so we see that 1 and 3 are also equivalent. There is a special terminology for, there are these two projections have special names. So in the setting of this proposition, if v in A is a partial isometry, then the projection v star v is called the initial projection of v, and v star is the final projection of v. Again, the picture illustrates what it means. So the initial projection projects everything onto H0, and the final projection projects everything onto H1. Our next goal is to prove a simple but useful result, which gives us a polar decomposition formula for invertible elements in any C-star algebra. Suppose that A is a C-star algebra. And let's introduce some notation. If A is an element in A, we denote by the modulus of A the square root of A star A. So A star A is positive. Let's recall that it is positive by Kaplansky's theorem. So it has a unique positive square root. So this is a positive element of our algebra. By the way, let's observe that this notation is compatible, is consistent with the functional calculus. Let's observe that if A is self-adjoint, then the modulus of A can be obtained from the functional calculus. We simply take the modulus of T, where T is the identity map of the real line, and apply it to A. is the identity map of the real line. This is immediate from the superposition theorem, because the square root of t, because the modulus of t is the square root of t squared. So the square root of a squared, now a is self-adjoint, the square root of a squared is just the modulus of t by the superposition theorem. So now we have the following proposition. This is the polar decomposition of invertibles. Suppose that A is a C-star algebra, and A is an element, A is an invertible element in A. I claim then there exists a unique pair UB, consisting of a unitary element little u, where u is unitary and b is positive, such that A equals UB. And moreover, B is nothing but the modulus of A. So this formula generalizes the well-known formula which expresses a complex number as the product of a number on the circle and the positive number. Well, let's start by proving the existence result. The existence. So we already know what B is. So B must be the modulus of A. And let's observe that since A is invertible, it follows that A star A is also invertible, because this is the product of two invertibles. And now the spectral mapping theorem implies that the square root of this element is also invertible. Well, the spectrum of this element is strictly positive, and the square root function doesn't vanish on the spectrum of this element, and the spectral mapping theorem implies that this element is invertible by the spectral mapping theorem. So it is invertible, and now we can look at this formula. So we want to prove this formula where B is the modulus. So U should be equal to A times the inverse of the modulus of A. And we now have to show that U is unitary. U star, first of all, it is invertible. It's clear from our construction. And if we multiply U star by U, what we get the modulus of A inverse times A star. This is U star. We multiply it by U, so we get the following. But A star A is the modulus of A squared. So after we multiply these elements, we get 1. And so U is unitary. Well, this completes the proof of the existence of our polar decomposition. Let's now prove the uniqueness. Suppose that A equals UB, where U is unitary and B is positive. Then A star A is B U star UB, but U star U is 1. So this is B squared. And so B, since B is positive, B is always equal to the square root of B squared, again by the superposition theorem. So for any positive element, we have this formula. But B squared is equal to this element, and so we get the square root of A star A, that is the modulus of A. So B is equal to the modulus of A. A is U times the modules of A, and so this implies that U is necessarily given by this formula. And this proves the uniqueness of the polar decomposition. Okay, so from now on, the set of projections and the set of unitary elements will play a special role. So let's introduce some special notation for these sets. So if A is a C-star algebra, then the set of all projections in A will be denoted like this. That is the set of all self-adjoint idempotents. If A is unital, then the set of all unitary elements will be denoted by U of A. So this is the set of all invertible elements such that U inverse equals U star, set of all unitaries. So let's observe that the set of all unitaries is actually a subgroup of the multiplicative group of invertibles. This is more or less clear from the definition. So the product of two unitary elements is a unitary element. So in particular, it acts on A by conjugation. And this naturally leads to the following equivalence relation. We say that two elements A and B in A are unitarily equivalent if there exists a unitary element U such that UA U inverse equals B. Well, clearly this is an equivalence relation on A. And let's observe that, of course, if two elements are unitarily equivalent, then they are similar. This is obvious from the definition. In some sense, the unitary equivalence is more convenient in the setting of C-star algebras, more convenient than similarity in the sense that, for example, it is more convenient for the following reason. So this group also acts on self-adjoint elements and on projections. So for every unitary element U of A, conjugation by U takes self-adjoint elements to self-adjoint elements and projections to projections, which is quite useful. Well, this is a little exercise, just a straightforward calculation to show that if A is self-adjoint, then this element UA U inverse, that is UA U star, is also self-adjoint. If U is just invertible, then in general this is not true. Well, and it's clear, we have already observed that unitary equivalence implies similarity. In general, the converse implication is not true. Actually, it fails already on 2x2 idempotent matrices. A simple exercise. If A and B are similar, then this doesn't imply that they are unitarily equivalent, even in the case where we deal with idempotents in the algebra of 2x2 complex matrices. So in general, the unitary equivalence is stronger than similarity. And a hint is the following simple necessary condition. If two elements are unitarily equivalent, then they have the same norm. But similar elements, the norms of similar elements are not necessarily the same. So in general, the similarity is, the unitary equivalence is stronger than similarity. But on the other hand, and which is quite useful, they are the same on the set of projections in a C-star algebra. So we have the following proposition. Suppose that A is a unital C-star algebra, and P and Q are two. Actually, we can consider any two self-adjoint elements. So we are mostly interested in projections, but the result is true for any two self-adjoint elements. So I claim that they are similar if and only if they are unitarily equivalent. And more exactly, if A is an invertible element which implements similarity between P and Q, that is A, P, A inverse equals Q, then if we replace A by the unitary which comes from the polar decomposition of A, then this element U implements a unitary equivalence between P and Q, where U is A times the inverse of the modulus of A. And we already know that this element is unitary. Well, let me prove this result. It's quite simple, and then we will stop here. So, so we take an invertible element A such that A, P, A inverse equals Q. Multiply this by A on the right, and we deduce that AP equals QA. And if we now multiply this by A star on the left, we see that A star AP equals A star QA. But QA is AP, so we can continue this as follows. This is A star AP. So we now see that A star A commutes with P. Now it's a simple exercise that this implies that the modulus of A also commutes with P. So a hint, well, this is a little exercise, but a hint is to approximate the square root functions by the square root function by polynomials. Approximate the square root by polynomials. So the modulus of A commutes with P, and so we see that U, P, U inverse, where U is this element, is as follows, is the following element. So U is A, the modulus of A inverse, times P, and the inverse of U is the modulus of A times A inverse. But now we know that P and the modulus of A commute, so we move this element here. It cancels with A inverse, and we get A P A inverse, that is Q. And this completes the proof. So we see that P and Q are unitarily equivalent. Сейчас, секунду, давайте смотреть. Ага, да. Just a moment. We want to show that this element commutes with P. AP equals QA, so A star AP, A star QA. Okay, so thank you. This is a reasonable observation. So an intermediate, we need an intermediate step. We take the adjoint of this formula, and we get PA star equals A star Q. Thank you. So we have this formula. Now what we do, we multiply this formula by A on the right. If I multiply it by A on the right, we see that the left-hand side will be PA star A, PA star A, and the right-hand side will be A star QA, like this. And so this solves the problem. So we see that A star A commutes with P, take the square root, and the remaining steps are the same. Thank you very much. So of course, to show that they commute, we first have to apply the star to this equality, and we get what we need. So as a result, we see that indeed P and Q are unitarily equivalent, which is quite useful. Okay, so that's all for today. Just a few words, probably I must explain where we are going to. So our plan is to give a more convenient picture of K0 in the setting of C-star algebras. What we're going to do is to show that if we take the standard picture, which is given in terms of idempotence in A, first of all, we can replace idempotence by projections. So the set of projections is smaller, and sometimes it is easier to work with than the set of idempotence. So we can replace idempotence by projections. We can replace, and it's already proved here, we can replace similarity by unitary equivalence, which is also useful. And at the next lecture, we will see that algebraic equivalence of projections can be described as another, in terms of another equivalence relation, which is called the Murray von Neumann equivalence. Again, it's a certain property which involves the involution on our algebra. So in summary, we will get another picture of K0, better adapted to the setting of C-star algebras, and defined in terms of equivalence of projections rather than of general idempotence. Okay, thank you. That's all for today.